Good morning, everyone, and good afternoon to those signing in from the more eastern parts of the world. We can begin with this webcast on the validation of a new AnyBody mandible model. So just to give you an outline of the proceedings for this session, we'll start with an introduction by the host. That's me. My name is Anant, and I work here as an application engineer at AnyBody Technology. And this will be followed by the main presentation by Michael Skipper Andersen, who's our main speaker for this webcast. He is an associate professor at Aalborg University. And for those of you who've been following Michael's career, you know that he has a good history with the validation of musculoskeletal models. He was in fact the winner of he was on the team which won the Grand Knee Challenge back in 2015, which was essentially a contest where you had to come up with a musculoskeletal model which can best reproduce in vivo forces in the knee joint as recorded by an instrumented prosthesis. So he has had a history with validation, but his presentation today will focus on a completely different part of the human body, namely the mandible, or the jaw as it's commonly known. He will start off by describing different ways of modeling the temporomandibular joint, and this will be followed by a rather interesting way of validating some of the model's predictions. We will have some closing remarks from me, and we will then be open for questions. So for those of you who are using this webinar system for the very first time, do familiarize yourself with the control panel which appears on the right side of your screen. You can expand or collapse this panel by pressing the red button. And if you have any questions, just feel free to type away in the questions panel. You do not need to wait until the end of the presentation to ask your questions. You can ask them as and when they arise, and we'll take it up with Michael at the very end. In case we cannot answer your question, in the interest of time, we will surely get back to you by email. For those of you who are also new to the AnyBody modeling system, this is a software for performing simulations of the musculoskeletal system when during different kinds of movements. It also comes with a model repository, which is essentially this, you can think of it as a library of models of different parts of the musculoskeletal system, each based on a different study that has been published, and which each of these models are put together to give you the full human body model, which you find in the repository as well. And these models are regularly updated and curated by the folks here at AnyBody Technology. The software gives a wide range of simulation options, which includes using motion capture to define your movements, using ground reaction force prediction algorithms, the specifying patient-specific anatomy using medical imaging data, and running man-machine simulations, which interestingly forms the topic of our next webcast, which I'll introduce at the end of this session. We see a wide range of applications for such simulations. While these are probably the research themes or the investigation themes which are most commonly encountered. The three main components of the modeling system are, of course, the human body model, or pretty much any body model in case you are interested in modeling animals. The motion and forces, these could be experimentally recorded, or there are some ways of synthesizing these motions within AnyBody as well. And of course, the model of the environment in which the movement is being performed. This could be something as simple as a flat walkway in a motion capture lab, or something a little more complex like an exoskeleton. So all these three are fused into one single human and environment model, which is what we could call the man-machine model. Following which an inverse dynamic simulation gives you the internal body loads, which are usually which are mostly, in most part, the muscle forces and the joint reaction forces. In case this doesn't form your final end goal, you could go ahead and use some post-processing tools such as finite element tools, and these AnyBody does have some plugins of sorts which can directly export your simulation data into the muscle forces on a bone into an FE simulation that you would like to run. Or in case you're interested in optimizing the design of your environment, you could run these sort of these iterative optimization studies within AnyBody as well. So with that quick introduction, I will now give the word over to Michael, who will enlighten us on this validation study that he has been working on.
Thank you, Anand, for the nice introduction, and welcome everybody. So I'll be talking about some fairly recent work we have done in developing a new mandible model in AnyBody, and also some validation of this model, which is actually a particularly difficult task. So the whole motivation of this work is that the understanding of the biomechanics of the mandible has multiple applications. So this could be like illustrated here on the slide, understanding of what happens when teeth are moved during orthodontistry treatments. It could be the biomechanics of changes to the skeletal system of the jaw due to surgical treatment of malocclusion in one form or the other, two illustrated here at the bottom. Or it could also be treatments for skeletal deformities, as illustrated on the right, for a young kid where the one side of the jaw is clearly asymmetric. And it would be ideal to use biomechanical simulations or biomechanical insights to guide these types of treatments and how it affects the loads in the face as a function of what treatment is performed. So one of the difficult tasks, or one of the challenges, is to model the temporomandibular joint. And for those of you who are not experts in this field, this is a joint that connects the jawbone or the mandible to the skull. And we have one on either side of the face. It is a fairly loose joint in that way that it allows in total 6 degrees of freedom between the skull and the mandible. And also in between the two bones there is an articular disc that is actually quite mobile, so when you move the jaw forward, the disc slides with it back and forth. If we also look at it from the bottom, it actually has an irregular shape, so it's not a clear, simple mechanical joint due to the geometry of the joint. So in the literature you can find an array of different models of this. For instance, one of my colleagues, Mark Sshaped, in 2007 published a model where they used a planar constraint model. So the idea was to basically approximate the movement that the jaw can do as a point on a plane on each side. So if we just look at it in 2D, it would correspond to a point up here on the mandible, only being allowed to slide along this line. This plane can of course be rotated in the 3D space, but just to illustrate it like this. Then they also assumed that the contact force can only be in one direction, and if there were ligaments in the model like this, it would carry the load in the opposite direction. There have also been other models that you can find in the literature. Here, a couple of them illustrated that has the same kind of feature, where they try to approximate the surfaces a little more accurately with these, what should we call them, S-shaped surfaces that are then in contact with a sphere that approximate the condyle of the mandible. And these are then included in forward dynamics based models where muscle forces are assumed as input, and then the contact force comes as a penetration of this sphere into this S-shaped curve, and the penetration depth decides the contact force. If we want to go one step further and actually include the articular disc as well, and also maybe even get close to the geometry that you can see on, for instance, a cone beam CT on MRI, then we can go one level down to detailed final element models, which will also allow estimations of stresses and strain in the cartilage. And to which level you need to model this, of course, depends on the question you want to answer in the end. But then what we have kind of envisioned, where the component I'll be talking about today kind of fits into this whole picture of possibilities. So basically we think that we want to start from medical imaging, in particular clinical cone beam CTs, which are fairly regularly obtained in the clinics for when you want to do surgeries for skeletal deformities on the mandible. It could also be assisted by MRI, but this is not as common. From this, you can segment out the geometry. Here just the skull has been segmented, but we could segment out the entire face. And then we can use this to define the geometry of a finite element model and also to define the geometry of a musculoskeletal model. Then we use the musculoskeletal model down here, which includes both the bones, also muscles and ligaments, to estimate the muscle forces, ground reaction forces, not the ground reaction forces in this particular case, but ligament forces and joint reaction forces as a function of movements that we put in. So which activities of the jaw do we want to analyze and what external forces are applied during this case. And then we can use those as the boundary conditions for detailed finite element models to actually analyze what happens in details in the articular cartilage, if that's what we're after. But I will, in this presentation, focus on some work we've done in the musculoskeletal model in this particular case. Yeah, so the aim was to develop and validate an inverse dynamic-based subject-specific model of the mandible, and it should enable prediction of muscle forces, joint reaction forces, and also joint kinematics. So the methods we did for this, we started from clinical cone beam CT that we obtained for one subject with a Newton 5G scanner. With that CT, we segmented out the skin surface, which you can see in here in the middle. I'll come back to that later, why we need that. So we segmented the skin surface, and then we also segmented out the skull and the mandible. We smoothed the surfaces that came out of the cone beam CT to later on use it for defining contact between the different surfaces. With that, we sat down to define the musculoskeletal model. And the first thing we did was to introduce muscles. So we introduced 24 hill-type muscles. Since this was a cone beam CT, you cannot see the muscle insertions on the images or on the segmentation. So we sat down with anatomical texts and also the previous model from Dessay et al. From 2007, and then tried to identify the same bony landmarks or the same bony locations in this particular model compared to what we could find in the anatomy books and also in the previous model. The mechanical properties, so the slack length, the optimum fiber length, and also the isometric strength and so on were adopted from the work by Kolstra and Van Eyden from 2005. And to model the temporomandibular joint, we introduced two models. So the model I already told you about, so point on plane, model similar to Dessay et al. In 2007 for comparison, which is, I think, is probably the simplest model we can do in this particular case. And then we tried to do something more advanced. So we introduced what we call a force-dependent kinematics model. And it's based on surface contact at the temporomandibular joint, and we also introduced models of the temporomandibular ligaments. I will, on the next slide, explain in more detail what we did here. Last but not least, we also defined an anatomical skull reference frame, which we defined based on a Frankfurt horizontal plane, so that we can represent both the joint reaction forces and the resultant joint kinematics that we get out in a shared anatomical reference frame and compare the results with the different models. So the first model we did was this point on plane model, as I said. So we introduced basically that one point on the mandible on each side, on the left and the right side, should always remain in contact with the plane defined similar to Dessay et al. On the left and the right side. And then also similar to them, we introduced a constraint that the mandible cannot move in the medial lateral direction. To drive this model in full detail and to fully describe the motion, this leaves 3 degrees of freedom between the mandible and the skull to still be defined, and how we got them I'll come back to. The other model is an advanced method we developed some years ago now, and the idea is to extend inverse dynamics with the possibility of modeling non-conforming joints. So the method in in its basic idea, can simultaneously compute muscles, joint, ligament, and internal joint kinematics at the same time. And the way it does it is by combining inverse dynamics and quasi-static force equilibrium. So in the model, if we go here, we introduced two elements compared to the point and plane model. So we took out the constraints from the point and plane, and instead we introduced the ligaments. So the temporomandibular joint ligaments on both sides, we approximated by 3 line elements on each side with nonlinear characteristics. So slack length is illustrated here with no force below a certain length, and then a polynomial toe region for low strain, and then as we have higher strain in the ligaments, we have a linear elastic properties of the ligaments. The specific properties of the ligaments are not really well known and not well described in the literature, so we did a parameter study to understand the sensitivity of our results to these. I'll come back to the details of how we did that. And then for defining contact in the joint, we introduced contact between the two surfaces. So we took the skull surface that we got out of the segmentation, and then we enlarged it by 1 millimeter to roughly, in a very rough way, try to capture the effect of the articular cartilage. This is of course not true, but there is a gap between the two bones, and we assume that it has the same shape as simply enlarging the skull by 1 millimeter. And then we used every single triangle of our STL surfaces to define the contact. So I think there should be an illustration of a series of forces down here at the top of the condyle, which is then the force in each of these nodes is proportional to the penetration depth into the other surface. So the deeper the penetration for a specific node into the other surface, the larger the force. And we assumed this to be linear elastic. Then we introduced FDK degrees of freedom in 3 directions, which were the ones we had before in the point and plane model. Those were the ones we wanted to control by the ligaments and the contact. So we wanted an FDK degree of freedom in the medial-lateral direction, and then also in the same direction as we had point and plane before on the medial and lateral direction, such that it's in principle the same remaining 3 degrees of freedom that has to be described for prescribing the rest of the motion of the mandible. So just in very simple terms, so what's going to happen in these FDK degrees of freedom is that for every time step throughout the analysis, we are going to find static equilibrium between every acting force in the system. So to have the joint in this particular case, we need to activate the muscles to a certain degree, which will push the condyle up here into the skull surface, and the ligaments will also be pulling to some degree. And then we want to find the movement in this direction until the force that is produced by the contact pushes against by the same amount as being pushed up, so to speak. So we wanted to also measure the movement of the mandible and also use the same measurement for validation. So to do this, we wanted to create a brace that can measure the movement of the skull and also measure the movement of the mandible at the same time. So compared to other joints of the human body, there is a good opportunity at the mandible to actually attach something directly to the bone, which you can do through the teeth, which you don't have the same opportunity anywhere else in the body. So this we wanted to take advantage of to do a direct validation of joint kinematics. So we got these braces manufactured. So a normal cast done by a technician, and then this plastic cast is the same as a restrainer done after orthodontist treatment. Then onto that, we glued some fairly stiff metal wires here on the left and the right side, and then we found some very lightweight foam. It's very rigid but very lightweight foam that we then drilled some holes into and then glued it onto. And then we attached in the 4 corners 4 markers that we could measure with the infrared cameras on 2 of them. Once we'd done that, we went to the motion capture lab, and we had 8 cameras from Qualisys sampling at 100 Hertz. And then, besides the 8 markers that the subject had on these 2 plates on the brace, we also positioned 9 skin markers on the surface of the subject. So we tried to identify some landmarks on the face of the subject that we could easily identify also on the reconstructed surface from the cone beam scan. Then the subject did 4 different tasks. So we did 4 tasks, and then 5 repetitions of each were used for the analysis that I'll go into a little bit later. So the subject did a cyclic opening and closing of the mouth to a half open position. So open to half, close again, open to half, close again, and so forth. The subject also did a cyclic movement from side to side, which is actually the one you can see down here with the reconstructed motion. So move the jaw to one side, move the jaw to the other. And then this we considered a repetition when you have gone from one side over to the other side and back again, and so forth. The third was an empty chewing movement without producing a bite force, because this brace that we have introduced, it does not allow the subject to really chew on it, and we don't have a way of measuring the force that is produced during the bite. So we wanted to have tasks without loads. And then we did a cyclic protrusion movement as well. In the results in a bit, I will only focus on the first 2, so the open and close and the side to side, just because they tell most of the story and also for the interest of time. So the last thing we did was we laser scanned these braces. So we used this Next Engine Ultra HD 3D scanner to reconstruct in 3D the brace, so we could use it in the model. And this has an accuracy of about 0.1 millimeter in the reconstructions. Since we unfortunately did not have a cone beam CT with the subject wearing this brace, which would have been the ideal situation, we somehow had to register the brace to the cone beam CT. And what we did was we took a trial in the motion capture lab where the subject was just sitting with his mouth closed, just like the subject was doing the cone beam CT. And then we used the markers to reconstruct the position of the different parts of the brace. So they would be positioned here. Blue is marker on the brace, and red is the marker in space, so they're sitting on top of each other. And then the same subject that had put on the markers during the motion capture experiment identified the same landmarks on the reconstructed skin as well as the subject could. And then we reconstructed the position of the skull and mandible based on that. And then we assumed that this is the relative position that these 2 components has relative to each other, and then used that throughout the rest of the analysis. The next thing was to introduce a parameter study of the ligament properties. So as I said, these properties are not very certain, especially the reference strain. So what is the slack length of these ligaments for this particular subject? Those we did not know. And also the stiffness of the ligament it's been described in the literature in some studies, but it's also not very well known. So what we did was we took a value that was in the literature. So this paper Chen et al. From 1998 reported that the ligament stiffness is 272.4 Newton per meter. So this is the one we put in the middle of our variation. And then we took half of it, and then we took 2 times that, as to have a range around what has been reported. And then for each stiffness value, we varied the strain, the reference strain, from -4% and up to 4%. So each combination, which in total gives 15 different combinations of stiffness and reference strain. And I'll report the mean and variation of this later on. So let's look at some results. So if we start with the open-close movement, and then we look at the kinematics, then the 6 graph here show, if we start at the top row, the left anterior posterior movement in this anatomical skull reference frame. We have the left medial lateral movement, and then we have the left superior inferior movement over here on the right. And then at the bottom we have the same for the right hand side. Then in terms of colors, the red curve is the reconstructed motion if we had no constraints in the model at all. So this is what the brace would reproduce on its own if we had no joint models at all. If we had used a point on the plane model, we would get the green. If we had used FTK, it would be the blue. And then it's actually very difficult to see, but the gray area is the variation that we see in the parameter study of the ligaments. And you can actually see, if you look at this variation, so the variations here in the different color is ±1 standard deviation over the 5 repetitions. So if we just take a look here, then it clearly shows that the variation from the ligament properties is smaller than the variation that we get over the 5 repetitions. So repeating the trial 5 times gives a bigger variation than the ligament properties can do. So if we then there are of course many metrics on how to compare it. I decided to only include one here, which is the squared Pearson correlation coefficient, just to look a little bit at the differences in shape. So if you start over here, then we actually both for the point on plane and also for the FTK are very close to the measured kinematics anterior posterior, and the same goes for both left and right. So 1.00 to 2 decimals, or 0.99, which is pretty close to perfect. If we go to the one on the right side, which is superior inferior, then we are also with both models very close to the measured kinematics, except FTK is actually deviating a little bit here towards the end of the movement and also in the beginning, and which is the reason why the correlation coefficient is slightly lower. And this is a little more pronounced on the right side than it is on the left side. And the good question why this is, it could be that the reconstructed surface from the cone beam CT is not completely accurate, or it's not good enough to capture the geometry, or it might be that the effect of the articular cartilage that we actually don't have in the FTK model is not well represented and maybe a little bit better captured with a simpler model. If you look at the one in the middle, then none of the models are really very good at predicting the medial lateral movement, but that's not very surprising since the movement actually happens in another plane. So there's not a lot of medial lateral movement in this particular case. If you look at the joint reaction forces, then even though the kinematics was fairly similar between the models, then this is not the same for the joint reaction forces. So if we look at the left side first, so this is again anterior posterior force, medial lateral and superior inferior, then for the left side they agree fairly well. So this is the squared correlation coefficient for comparing the two curves. They're fairly the same. There's something with the magnitude, so they don't agree completely on the magnitude on the anterior posterior direction, which is, I don't think is a surprise considering that the point on plane model cannot change the direction of the reaction force because it's completely fixed depending on the slope of the surface. The superior inferior force, they agree also in shape again, but also they don't completely agree in magnitude. And I think this is probably, so the missing force over here in the green is probably what is over on the other side, so it's just the force that is rotated a little bit. The same is not the case for the right side. So if you look at the anterior posterior force here, then the subject's geometry is clearly more flat on the right side than it is on the left side. So the assumption of this point on plane is not as good on the right side as it is on the left. So here we see a bigger difference. However, we don't know which of these two are correct because we haven't actually measured the joint reaction force, and there's no tool available to do this in any simple way at this point. Yeah, but then again, the superior inferior force, they agree really well, and there's a I think in the mean curve they actually do agree fairly well, and because the magnitudes are low, that's why the correlation coefficient is low, because there's a little bit of variation around 0, but they don't vary in the same kind of way. If you look at the kinematics from the side-to-side movement, then the story is basically the same. So if we, again, for the anterior posterior and the superior inferior, the two models agree quite a bit with the measured kinematics, so correlation coefficients above 0.9, actually 0.96 for both left and right superior, left and right anterior posterior, and so also for the left superior inferior. However, there's again a mismatch on the right superior inferior, which again might indicate that maybe the cone beam is not completely ideal for this situation. So, but it's still, there's fairly small movement, and it seemed to be captured a little bit worse by the FDK model on the right side. Same story with the medial, that the point and play model does not capture the movement very well, which is very clear because it was not allowed to have any movement at all, whereas the FDK model actually captures this medial lateral movement quite well doing the side-to-side movement, which is not captured otherwise. In terms of the reaction forces, they actually agree a little bit better, especially in the superior-inferior direction compared to the open-close. So here there's not a large difference. Certainly if you look at the force magnitude, they're almost the same. There's a little bit of a shift in the superior-inferior force here, but overall they agree quite well on the forces. However, this is not the case for the medial-lateral force or the anterior-posterior force. And I again think this is because the point and plane model is a little bit too simplistic in capturing how the force direction will change as a function of the movement in the jaw. So with that, I would like to conclude. So we have developed a subject-specific musculoskeletal model of the mandible. It in general showed good estimates for joint kinematics, whether we used the point and plane model or we used our FDK model. However, we did actually see differences in the estimated joint reaction forces in this case, so which clearly shows that this particular musculoskeletal model is sensitive to the modeling of the joint, and it's not enough that the kinematics agree, that it's not enough to have the same joint reaction forces. However, there is still a big challenge to actually validate what is then the correct set of forces in this particular case. And as far as I know, there are not any instrumented joint prostheses available for the mandible at this point that we could use that like has been available for the hip or the knee to getting more insights. But we need to work on this. Yeah, so the last point here is that the joint kinematics and joint reaction forces were not more sensitive to the variation in the ligament properties than repeating the task more than 5 times, which is of course good because these properties are very uncertain, but if the model is not too sensitive to them, then we don't have to be too worried about it, I would say. It would have been another story if the model was very sensitive to these parameters. So future work. So the first is to improve the TMJ model and the FDK model. I think it will not be too difficult to take it one step further and get a simplified model of the articular disc in there, either as a floating body in one form or the other, which I think will take it one step further and probably get even closer to the measured kinematics with this FDK model. We also need a method to automatically estimate muscle origin and insertions. So right now it was a manual task of actually identifying these points, but it would be ideal to automatically get that the minute you actually have the geometry. And there are methods available for that. We have implemented some in our lower extremity model, but we just need to set up a similar workflow to do it in the mandible as well. Then of course this was a talk based on one subject, so we need to validate it on more than one subject to understand how the results vary across a range of subjects. And then of course the model is not very useful before we start applying it for actually studying some biomechanics of pathological cases. So with that, thank you for your attention, and then I will give the word back to Anand.
Thank you, Michael. That was a very interesting presentation indeed. So this would be a good time for, I'm pretty sure all of you would have some, there would be some things in the presentation that you would like to know more about. So it's a good time to collect your thoughts and just ask away. You could type your questions into the questions panel. So just a few closing remarks. The next webcast is scheduled for the 15th of March. And this is on the simulation of on man-machine simulations, as I spoke about shortly during my introduction. And you could check our YouTube channels for previous webcasts. Some webcasts which might be relevant to the work that you saw that was presented by Michael today. There are 2 webcasts or maybe 3 webcasts on non-conforming joints, such as the Temporomandibular joints, which basically aren't as simple as something like the knee joint, which you can just model as a hinge, for example. So you have 3 of these webcasts from 2011. So please feel free to go back and access them using the YouTube channel to know more about these models. And on our website, anybodytech.com, you can look out for more events, such as new webcasts that will be announced from time to time, conferences where you can come down and meet us, and publications made using AnyBody. And of course, we also do have some job opportunities which are listed on the website. So if you are on the job market, please do check them out. And in case you're interested in knowing more about the AnyBody modeling system and its programming language itself, you can visit www.anyscript.org. So with that, we will now go into the question and answer session. So we do have a few questions here already. Let me just bring Michael in.
Thank you.
Yep, thank you for the talk.
You're welcome.
So we can now, let me go through the first question now. So is there any study in literature where the tensile force when opening the mouth is measured?
That is a good question. I actually don't know if there is. I know there are some measurements in the literature about bite forces.
Okay.
So the load that you can apply while biting on different things, but should be possible to measure the other way. So if the net force that you can produce when opening your mouth, that must be possible to do.
Yep.
But then the question is, how do you bring this external load into what actually happens in the jaw, what happens in the muscles? So I will say something about the net loading state, but yeah, it's a good question how you would use that to validate that.
Probably if when you have people wearing braces and they have these, I've sometimes seen them have these elastic bands running across. So you probably just have when you know the stiffness of the elastic band,
True.
probably have 2 marks on them and then just measure the strain.
True.
That, I don't know. That might be one way of
true.
finding out the tensile forces.
Yeah, true.
But yeah, thank you for that answer. So in addition to musculoskeletal modeling, would you be interested in modeling the blood flow in a static posture? Do you think that would have any impact on or do you think that there's any value in combining these simulations with musculoskeletal simulations?
I think that depends on what the question is. So these type of models here will tell you about what the net forces and loads are going through the system.
Okay.
But of course that will affect also the blood flow. I
Okay.
mean, so I'm not an expert in that area, so there might be a way to combining what happens to the blood flow in your face as a function of the way you chew or what's going to happen in your face. But it's not an area that I know much about. So but it might be a good idea to try out if you have an idea.
All right, cool, thank you. So based on your results, which of these 2 models would you say is better, quote unquote?
Yeah, that's as always a difficult task. I think if you just have to look at these results as such and look at the metric we have as output,
Yep.
then I guess the point on the plane model is the most accurate of the two. I mean, just if you want to look at it from a quantitative point of view, so what does the results actually show?
Got it.
However, there is an assumption made in that model is that the plane is in a certain direction with a certain orientation.
Mm-hmm.
And if you have some very large deformities, which could happen in some pathological cases,
Yep.
it might not be possible to assume this.
Yep.
So, and then I think the good thing about the FDK is that we don't make any assumptions like that. We
Got
really
it.
have to try to capture the geometry of this specific subject, and then try to also include the elastic properties that this subject might have. So I think there's an advantage there, but I think this particular subject with the specific geometry, I don't think that made a big difference.
Got it. Thank you. So if I understand right, the way FDK works is that it essentially sort of tries to fine tune the instantaneous state of the joint, so that all your muscle forces and ligament forces are in equilibrium, right? So it's perfect static equilibrium.
True.
So do you think this is an important assumption for something like simulating movements?
I actually think it's a fair assumption.
Okay.
Because I think if you look in the graph doing these, there's no indication that there's dynamic missing. I mean, it's not like there is any of the curves where you look at the measurement and say that it has some dynamic component that must be missing in the simulation.
Okay.
And I think it's because there's a lot of damping in the joint. So if you actually wanted it to solve this like a forward dynamics problem, you would have to introduce a lot of damping as well. So then I think you would get close to the same solution one more time.
Got it. So probably when it comes to more snapping movements of the jaw, that's probably
true.
when it might start showing some sort of dent in its capabilities.
True.
So to wrap things up, one final question that I'm going to try to sneak in here, and I'm going to be a little selfish and try to sneak in a question of mine. So now, just like most of us working in musculoskeletal modeling, we all like to think of our research as some sort of building towards clinical applications someday, so probably 10, even maybe 10, 15 years down the future. So first of all, what sort of applications would you see for such a model in a clinical setting? And secondly, if you think about dentists, they aren't the kind of people who would necessarily understand forces and kinematics and kinetics and so on. So how can we recast this information? So what's the best way to present the results of such a musculoskeletal model so that it could be of maximum relevance in a clinical setting?
True. Let me answer the first one. Where could this be relevant, and what clinical application do I see for this? Then I think the first one in the beginning is, I mean, in the planning of surgeries. So surgeries that involve changing the shape and so on of the mandible in one way or the other, or the skull.
Yep.
For instance, when you want to correct for malocclusion.
Okay.
I have actually talked to some surgeons which are very interested in this type of simulation, because what they do now is basically with the aim of making the face look right. So they aim to make it look like make it look as asymmetric. But that doesn't necessarily mean that the biomechanics of the chewing function afterward is optimal. So there might be a way to use these simulations to get insight of what is then optimum from a biomechanics point of view.
Got it.
Yeah, and to answer the other one, that's I think is a very good question, because this is something engineers do, and they understand forces and moments and stresses and strains. But then how do you then translate that back into something a clinician would understand on an everyday basis?
True.
And then I think one way would actually be to bring it back into comparing it to a normal, and then bringing it back to scales or something like that they normally look at it from a clinical point of view.
I understand.
So to try to bring it into to the same kind of language that they normally use in the clinical.
Got it.
Because I think you're right. We can't come and say something in moments and forces and so on.
True.
And that I don't think will work.
Great. Thank you. Thank you for that great talk, and thank you for answering all our questions.
You're welcome.
And any unanswered questions will be, we're sorry to be rushing off right now, but we'll surely get back to you by email. So on that note, thank you, and I hope to see all of you for the next webcast on the 15th of March. Thank you very much.